So good morning, welcome back. So having finished the formal part of the course, we'll have a rather informal Chapter 6, Applications. And the first application we're going to look at is quantum mechanics on curved space. So in this section and the next few we're going to discuss, I would like to change the character of the course a little bit from telling the truth or telling the existing structure to discovering together how in formulae and expressions and methods and folklore in physics that you all know how we recognize the structures we found, because that's good training in order to apply the whole stuff. And well, if we look at quantum mechanics, let's look at it in a rather naive way, and that's the way it's presented usually in introductory courses. So in quantum mechanics, we discuss wave functions. And such a wave function, psi, is, if we talk, for instance, about some position space representation, we think about it as an element of some space L2 over some r-dimensional space Rd. So in most physics applications, of course, R3 as the underlying physical space. And this L2 space, well, actually, we should talk. Well, there's a number of issues here, and it's the question. So let's call this Roman L2 Rd, and let's construct this L2. So let's first have a script L2 of Rd, and let's say that's the space of all psi, which are complex valued functions on Rd, such that a certain integral converges, namely the integral dx psi absolute value squared converges. Okay. Now, this space is not this space, because in this space we only look at the equivalence classes of such guys, where it's ensured that the two functions only differ. So any two elements in here are to be identified in here if their difference has a vanishing integral of this type. Okay, so this is one of the issues. The other issue is that here you need a Lebesgue integral in order to make this really work, rather than a Riemann integral, and so on. So there are lots of things at this point to be said. However, this is far not all the subtlety one needs. And I only mention this because I want to disregard this. So we're not going to look into these subtleties, but they should be mentioned once. So if we now look at some position space representation, or some representation in general, we wish to have operators. We need self-adjoint operators. And they should act on this space L2, but it will turn out they can't. So let's call them Q, I, supposed to act on L2 linearly, and Pi, supposed to act on L2 linearly, I equals 1 to D. Okay, and they're supposed to be self-adjoint with respect to an inner product, which in a sense are already used here, phi comma psi d dx psi star of x phi of x. Okay, and they're supposed to be self-adjoint and satisfy. They're also supposed to satisfy the commutation relations that the Qi, Qj is 0, the Qi, Pj is delta ij, and the Pi, Pj again ought to be 0. And here you may insert h bar, but let's say h bar is 1. Okay, so this is certainly the standard folklore of what you want to do. Now, it's also the standard folklore that you can represent this operator Qi on psi, then called the position space representation, by just multiplying with the ith coordinate here. It's this guy, and the pi psi can be represented by minus I h bar, which we set to 1, del I psi of x. Now, the problem with this folklore is that if you have a square integrable function and you derive it, well, can you derive any square integrable function? No, you can't, because you could have a function that just consists of little boxes, you see, and that can't be derived at every point. So clearly, this is the wrong domain if this guy is supposed to be represented like this. Okay. Now, let's assume we have a square integrable function and we multiply it by a coordinate it depends on. The result needn't be square integrable anymore. Okay? It's also pretty obvious. So it's also clear that this here is the wrong target. Okay. So all of these things are taken care of. So these issues, issues of domains and targets. And you see this has a bearing on what self-adjointness is rather than just hermeticity. Issues of domains and targets can be taken care of. And that's using the Gelfand triple. So there you look at the space of Schwarz functions, which are certainly square integrable. Okay, and but however, these again can be embedded into a dual space. So in linear functionals of a certain type, well, on this Schwarz functions, and then actually you can first define operators here. So you can define this from S to S and S to S. That works because they're very fastly decreasing and have nice properties under arbitrary, often differentiation. And however, the dual space, the L squared can again be embedded into the dual space, and then you can lift these operators that you define on S, you can lift them to here, and then you can do everything you want to do. And this is the space, so these are the Schwarz functions. Schwarz functions and or Schwarz space, and this is the space of tempered distributions. So in my statistical mechanics lecture, I explained this at some length. So if you want to look that up somewhere in some lecture notes. Okay, why am I telling this? I'm telling this because first of all, it summarizes what is usually said. It points out some issues there. But I want to use this as a kind of a waiver. We're not going to look at this. We could look at this, but this has less to do with differential geometry, but more to do with functional analysis. So we're not going to look at this. This can be looked at the same time. We disregard this in order not to obscure the discussion too much. Okay, so this will be not the issue here. Okay, what will be the issue here is the point that it's very often said that A the wave function is exactly this. The wave function is a function on some physical space, a complex valued function. Well, it turns out that this is an untenable point of view. This is simply not correct. So it's already the starting point that causes us some trouble. And from this starting point onwards, one is usually led to making all kinds of claims like, well, this is the right quantization rule for the operators, okay? But it only works if these guys represent the position in Cartesian coordinates, and these are the corresponding momenta in Cartesian coordinates. That's also wrong. But in order to solve this, one has to get rid of this idea that wave functions are complex valued. Okay, so now let's discover what the problem is. Okay, so first, however, we quickly check that, for instance, this represents this P here and the Q, that they have the right properties. So the standard view, or the standard view works as this. So first of all, this Pi, which is the minus I, well, Pj is better, the minus I del j operator acting on some suitable restriction of L2 in this case, is self-adjoint with respect to the inner product we defined. Let's very quickly write this down. So we have psi and pj phi. What is to be shown is that this is the same as pj psi comma phi. Okay, so this is quickly done because this is just this integral here. We have a psi star of x. Now comes a minus I times del j acting on phi, and then this whole thing being evaluated at x. Now, I said I act on, well, maybe I, okay, acting on these test functions that sufficiently quickly decay. We do now an integration by parts. We shift this over to all the other factors here, but there is just one in this case. So there is a minus from the integration by parts. There's a minus I anyway, so there is an I. Okay. Then there's a del j psi, which is then starred, evaluated at x, and there remains a phi of x. Now this I that I have left over, however, can be pulled into this bracket of this object that's being starred. Then, of course, it gets a minus I because it's being starred. But now it's pretty obvious. This is pj psi comma phi. So indeed, this choice acting here, these are Cartesian coordinates on Rd. This guy satisfies this self-adjointness property, and so does the Qi that just acts by multiplication. It's also self-adjoint. So everything is fine. The second thing we should check is the commutator. Well, you know, so you take the Qi with the Pj, okay, and it's always clever to apply this to some function here, and then you get the Qi minus I del j acting on psi minus I, so plus I del j Qi acting on the psi by x, sorry, called these guys x, and now it's clear. This guy back here, this has two parts. I delta ij psi of x plus I xi del j psi of x, but this cancels against this first. This cancels against this first part, so all that's left is I delta ij as claimed. Okay? So everything is absolutely simple and easy. So why do we worry? Well, we worry because we're differential geometers, and one thing we do not want to take for granted is that we are restricted to a particular choice of coordinates. Why would we do that? There is no detector that detects in physical space coordinates. Coordinates are a product of our imagination. So let's, in our discovery here, consider the case where instead of the coordinates x and y, we use coordinates r and theta in the plane. So let's consider r2, because we just want to discover something. We'll do it more generally once we got the idea of what's going wrong and how to repair it. So let's consider R2, but let's choose to coordinatize it by, well, strictly speaking, R2 without the origin. And let's coordinatize it by r and theta by the usual polar coordinates. How does the whole business present itself now? Now, claim. I can now introduce Q alphas, position operators, but now alpha runs over r and theta. Instead of 1 and 2, it's convenient to write it like this. Well, this would be r if alpha is r. Well, it's a little silly. And this is theta if alpha equals theta. And the p alpha, I set minus I del alpha, which again is supposed to mean that it's minus I d by dr if alpha is r, and minus I d by d phi if alpha is phi. I claim that this satisfies, or these satisfy, the commutation relations. Q alpha p beta is I delta alpha beta. And you can calculate this, and it's correct. This is true. Of course it's true, because the only thing I'm using here is that if I derive one coordinate with respect to itself, I get a 1. If I derive it with respect to another one, I get 0. And this is 1 in the other. And these partials acting on these coordinates this way absolutely satisfy this. Okay? So the problem, there is no problem in going to polar coordinates as far as the commutation relations are concerned if I choose this representation. And we want to choose this representation. Okay? The problem, however, comes up. So this is no problem. However, what about the self-adjointness? Of the Q alpha and the P alpha. And there we're in for some surprise. But first we have to write down for these abstract wave functions. And we're still adhering to the idea that this is a complex valued function, otherwise our calculations don't apply. If we now write down our two-dimensional integral, of course it's dr d phi times r, because this is the dx dy. Using the Jacobian of this coordinate transformation, we get this extra factor r, right? Okay, so we have this, and then we have here a psi star that depends on r and theta. We have a phi that depends on r and theta, and this defines a proper inner product. So there is no problem with this guy. So this is a proper inner product. So it could be that there is an issue here already. Well, there isn't. How would there be? Because this is exactly the same value. You see here we're not talking about coordinates. Here we're using the representation. Here we're using the abstract wave functions. It's exactly the same integral as, well, not this one, but as the one for the inner product I wrote down before. It must be a proper inner product. Okay? Nothing has happened because we legally changed coordinates by introducing this guy here. So still, everything seems to work quite fine. So, well, this, however, was a little premature because everything was still fine. Now, really, however, using this inner product, we can now check whether, for instance, our P alpha is self-adjoint. Okay, so what do we check? Psi P alpha with respect to r, with respect to theta, phi. So what is this? This is the integral dr d theta r. That's our volume form. Then we have a psi of r and theta. And we have a minus I del alpha phi of r and theta. And this P alpha already proved its worth by satisfying the commutation relations with the x. Sorry, with the r and the theta as the coordinates. So we think it's just a matter of routine of doing this. So let's follow the same recipe as before. We have here this derivative, and we want to get rid of it because we want to make this phi free of any operator. So we use integration by parts to pull it over. But now there's an important difference to before. The important difference is that now if we apply the integration by parts rule, this guy, as always, acts on the entire rest, but now this r here, coming from the change of measure, will also be affected if we pull this over. And that will make all the difference. And that is where a serious problem will arrive. And that problem we're going to have to solve. But let's first see what the problem is. So put a minus there from the integration by parts. Then a minus I is a plus I. Let's keep track of it like this. Then we have a dr d theta del alpha of r psi. The whole thing will depend on r and theta. And there will be the phi freed of any derivative operator action. I'm sorry. And here, of course, we need a start psi that we had before. We can still star here because the r is, of course, real. And we can also put brackets before we star the whole thing and pull this guy in with a minus I. And we already see what the problem is. The r should be out here in order to yield P alpha psi comma phi. But the r, unfortunately, is in here after this derivative. Okay? So this is, generically, this is not, well, let me write down what it is rather than what it is not. Okay, so now let's apply this derivative to this factor and to that factor. And that will, of course, depend on what the alpha, what value the alpha takes. So let's take case 1. Let's say alpha is just the theta. Okay, we're dealing with the theta coordinate. In this case, psi p theta phi is, well, in that case, this r is not seen by this derivative and can be pulled out. And then everything is fine. This p theta is indeed self-adjoint with respect to this inner product. That's not the problem. But what about the other case, too? The alpha being the r itself. Well, in that case, we have psi pr phi is the integral. And now I use the product rule here and split this into a part we would have expected and a part we didn't expect. So using the product rule, I have dr d theta r. So I do not act on the r. Then I have minus I del r acting on psi, the whole thing being starred and the function of r and theta, and phi of r and theta. So that's good. So that's exactly what we want. We wanted if the I were self-adjoint, but you see, because of the product rule, there is an extra term. Plus, well, okay, so what's the extra term? The dr acts on the r, and all that's left is the psi star itself. So, well, it's minus I times the integral dr d theta. The r has vanished by the action of the del r, and there is just a psi star of r and theta and a phi of r and theta. Okay? So, but you see the problem, there isn't even a real, this is not the proper volume form here. There is an r missing, so this is not psi phi or something. This is just some other extra term we just don't want, okay? Because it renders this PR non-self-adjoint. What do we do? So this is an observation, and at this point one is inclined to give up. Well, that's the first point where one might give up, because one says, okay, we satisfied the commutation relations, but somehow these non-Cartesian coordinates, in Cartesian coordinates it works all fine, these non-Cartesian coordinates, they set up the whole thing, and somehow this simply doesn't work. Okay, so the idea one might have here at this point, and it's nothing more than an idea, is to say, well, hang on, these partial derivatives acting on this function phi. Well, why might we give up? So discouraging. Let's say discouraging. It's discouraging because one thing is ingrained on our mind by many lectures, and that is that psi indeed is a map of this type, suitably restricted to be falling off sufficiently fast, and square integrable and whatnot, and so with all kinds of restrictions, but ultimately it's a complex valued function here, and that's the name wave function. And the solution to the riddle is to get rid of exactly, so solution to our problem, namely to use other than Cartesian coordinates, any other than Cartesian coordinates, a solution to the problem is to forget about this. And now you say, well, how would we forget about this? Because this is the basic idea of quantum mechanics. It's the first line in almost any quantum mechanics textbook, right? And of course, as differential geometrists, we have another idea. It could be that this is just locally true, so vague idea. What if psi is a section of a C vector bundle over RD? Okay? So the idea would be that if this is RD, which I just draw in one dimension, of course you can also do this in one dimension, then at every point I could attach a fiber, which is the vector space C. It's a vector bundle with suitable bundle projection and the whole shebang, right? And the idea, so that's of course a local picture, it looks like this locally, and that the psi is just a section of this bundle. So if this is the bundle total space, the idea would be that the wave functions are a section of this vector bundle. And locally, yes, that looks like a function over RD. But what's the difference? What's the difference if we turn to this view, which has this fantastic property of being almost the same as the standard view? Okay? So, I mean, it would be ridiculous if you want to solve a problem by deviating so far from the standard view that has nothing to do with it anymore. Right? So it's the subtlety of considering it like this. What does this yield? Well, the idea is you can now consider this bundle E as an associated bundle to, well, you could consider this as an associated bundle to many, many principal bundles, but which is the principal bundle of interest if we're dealing with general changes of coordinates? What's the bundle of interest? Well, it's the frame bundle, because if I can arbitrarily change coordinates on the base manifold, I induce by this changes in the coordinate-induced frames. Okay? And I want to study how this guy behaves and what happens if I change coordinates from one system to another system, which also means I change frames. Okay? So consider this as an associated bundle to the frame bundle. Lm pi, well, then this is pi e, pi down to m, and m is Rd. So this is the vague idea, right? Now, still, our feeling is, why would this possibly help us? Why could this help us? I mean, what's the difference here? Well, you know that if you have a frame bundle, you can establish on the frame bundle a connection. If you have a connection, you can define a covariant derivative on sections of any associated bundle. Right? And then you have a covariant derivative acting here. Do you remember how these sections of such a bundle, an associated bundle, can be represented? They can be represented as C-valued functions, but not on the base space, but as C-valued functions on the total space of the principal bundle. We had this theorem. You remember that? Okay. So saying that psi is a section of this associated bundle with fiber C is the transition to saying psi is a complex valued function, once again, but not on this space. So let's say the section is shown like this, but not on this space, but it can be represented as a complex valued function, but on the total space of the associated principal bundle. Okay? So remember, we had a theorem to that effect. Aha. And then, because we're on the principal bundle, we can use there the covariant exterior derivative of psi. You can take the covariant exterior derivative of psi, and you know that, well, in any case, one could show that this is d psi plus omega wedge psi, but psi is just a function omega psi. And you know that in this wedge, the omega actually acts from the left on the psi, and this is the left action of the GL dim M group, so in this case GLD, R group, that I need to establish on these fibers in order to make this an associated bundle. Aha. Okay, so this is a very vague idea. It comes from this, that I say I want to get something like this locally at least, but this is a slightly different way, a subtly different way to implement this. It leads us here, it leads us to this exterior covariant derivative. Now this is on the principal bundle. We can then pull this down by choosing some section to the corresponding Young-Mills field and so on. 1 second. Okay. And we get from this, by pushing it down to the base space, we get a covariant derivative of this psi. Aha! And now this is very different from what we did so far, because so far we only looked at this part. So far we represented the P as minus I just as this partial. But first of all, this was on the base manifold, not on the bundle. And second, it acted on the psi as a function there. Well, as you see, you can actually, you have an extra term if you start considering this psi as a section of the C bundle. You can generate, you must have an extra term in order to have a geometric quantity. So this is the very vague idea, which we're now going to forget again. The only thing we're going to see is that we modify our definition of the momentum operator by allowing an extra term, and we'll determine from down-to-earth physics calculations of what this guy must look like. And so we'll slowly, so this is just a cloudy idea, okay? But now once we had this idea, we store it, we take some inspiration from it, we go back to the nuts and bolts business on the base space, and we try to finally come up to this whole picture, okay? But the idea is modify this partial derivative, because this partial derivative supposes this is a function, and even if we make this a covariant derivative on a function, a covariant derivative acts like a partial derivative. It must be the section of some bundle in order to warrant this extra term. There was a question.
Yeah, I've got two questions. First, is there a difference between pi e and pi? No.
Yes, yes. This is the projection from in this bundle where over the base space M we have at every point a fiber C, and this is the pi where over the base space each fiber, this LM, each fiber is the fiber of all the frames you can have here, all the tangent space bases, and the pi takes you down here. So it's a pi on a totally different bundle. Pardon me?
And the pi takes me then to RD.
Takes you to RD, yes.
Okay.
Yes.
And then actually a second question is, why do we do this, why do we do this construct the other way around, like you just said, that we take our calculation and then we sort of try to feed this idea into the calculation other than working from the idea back to the calculation? You get what I mean?
Yes, because this is what we learned, and that's what we use and what gives us the transistor and whatnot. Okay, so this is the quantum mechanics that works.
Yeah.
And we have a rather highbrow mathematical idea here. We're claiming that you have to get rid of a cornerstone of standard textbook quantum mechanics, namely that the wave function is a function, complex valued function on the physical space. We want to throw this out. Now, if you start here, well, can you write down what the connection is right now? No, me neither. That's the point. So this is the nature of research. So we kind of start at some point, we try to achieve something, we have the idea we must make this independent of coordinates and so on. And this is, as I said, just a vague idea. That's what's in the back of my mind. Let's try, we have an extra term here. We use a derivative here. No, this is given by a derivative operator, and we produce an extra term. Question. Had we taken, instead of this derivative on a function phi, had we taken a covariant derivative on a section of a C bundle, very roughly speaking, which then produces an extra term, would this extra term, could that have been used by appropriate choice of omega? Well, you have to push, this is still on the principal bundle, you have to push this down, but that's another issue. By an extra term here, maybe this extra term could have cancelled this term and everything would be fine. That's what we're going to try. But we're coming from a base space picture, okay? And this is already on the frame bundle. And we'll connect them eventually, but at the moment, we play it safe, we only do stuff we fully understand, rather than starting to guess stuff here and trying to work by trial and error whether we arrive at the right thing. We rather come from something we know that works. It's quantum mechanics in Cartesian coordinates. We know that works. So what we do, we start from what works, then we apply mathematics. We do only, if you want naive, but we only do valid operations like change of variables and integrals and so on, and we try to arrive here. But in order to go somewhere, you need to know what direction you go. So this is kind of this thing. We're going about this direction. This is the vague idea. But now we start here and we see how exactly we have to go there. Okay? So, fine. Okay, so we have this. So let's use this idea and let's rather simple-mindedly propose a different thing, namely propose that P alpha be represented by minus I and something we could call a covariant derivative, nabla alpha. And so this is supposed to be a covariant derivative on a C, well, on a section of E of this bundle. And you know, the point is with covariant derivatives, it's on the problem sheet, a covariant derivative acts on a function. Now, f is really a function. F is really a function from Rd to C, say. It acts like a partial derivative. That's one of the properties of covariant derivatives. More abstractly written, if you have any tangent vector to the base space on a function, this is just the action of the tangent vector on the function. We all know this. However, if a covariant derivative acts on a section of a bundle on which it is defined, then this is simply not the partial derivative, but then this can be written, or at least we write it at this point like this. There is an extra term. And if this is a C, so there's an omega alpha acting on the sigma, right? This is a one form, and this is the Young-Mills field, because we are down on the base manifold. Okay, so this is what we have here. And so what we're going to do, or trying to do, is we assume that this derivative here is not a partial derivative acting on a function, but a covariant derivative acting on a section of a C-line bundle. Okay, so how far do we get with this idea? Well, let's try. So we take the problematic, well, we take both. So we take psi, comma, P alpha again, acting on phi, equals dr d theta r. That was our volume form. Psi star of r and theta, but now the derivative here is minus I times del alpha. It's the trivial action, phi, plus some omega alpha, which we're going to determine phi. This is this guy. And now we do precisely the same calculation. We pull this over to here. This is dr d theta. The minus I becomes an I because of the integration by parts. Del alpha r psi start r and theta. Okay, so we pull the I in here again. That's a minus I. I'm sorry. I pull the I here and we do this. It's the same thing. And then the phi is free of any derivative action. And then there is an extra term, an extra integral, minus I times dr d theta r psi star of r and theta omega alpha, which will depend on the point r of theta, and phi of r and theta. So we produced an extra term here. This extra term comes because we used the covariant derivative and we gave up the idea that this is a wave function, but rather a section of a C-line bundle. Now again, we have these two cases. We have the case alpha equals theta, and we already know that this integral here then simply is psi p theta psi comma phi. Yeah, well, and then this term is not needed. It would destroy what we want to achieve, because we want to achieve that this equals this. So in this case, therefore, choose the omega theta, the omega where alpha equals theta, choose this in these coordinates to be 0. But then we have the case alpha equals r, and then unfortunately I erased it, but you know this also gives you a PR psi comma phi, but there was a correction term, which maybe you could tell me again what the correction term was we had before for this. Minus I. Yeah. Yeah. Exactly. Thank you. Yes, that was it. We have this minus I, and then we have another minus I. Aha. And that minus I was correct? It was a plus I, because this guy here is starred. I think it must be a plus I. You're positive? Okay. And then now here we have a minus I integral dr d theta r. So there is an r, there isn't. Otherwise, it's the same psi star r theta omega sub r, because we're in the case alpha equals r of r and theta, and phi of r and theta. Now, it doesn't take a big genius to see how to choose omega r to make this work. Namely, omega r needs to be chosen as, in order for these two terms to cancel. One over r, or not? Omega is 1 over r, then this r goes, and these two integrals are the same, correct? Well, the same up to a sign, and hence cancel. Okay. Aha. So we now achieved by a modified definition of this p, we achieved to get rid of the extra term in both cases by choosing the omega appropriately. Now one might worry whether this change of the p here now, however, destroys the commutation relations. This could, of course, be the case. Well, let's check that. So what we found is that p alpha is minus I del alpha plus omega alpha, well, if acting on a wave function, psi, and this whole thing in coordinates r theta, so that this is the tangent vector index to the r theta coordinates that are being induced. But let's not forget that so this is for any psi being a section of this bundle we imagined. I mean, this bundle I'm going to use because that's what it is. Well, strictly speaking, yeah, well, okay. Well, strictly speaking, this is not quite correct. So this psi is not this psi. Okay, so let's take a capital psi, which is a section of this bundle. Okay? And we said that a section of this bundle can be equivalently represented, so I'll use the same symbol, can be represented as a fiber valued, in this case a C fiber valued, a C valued, but now really function, but not on the base space M, but on the principal bundle associated with it. We think of this being associated. And now this psi here is supposed to be the pullback under a chosen section on this principal bundle, where sigma is a section of the principal bundle. So pi after sigma is the identity on the base space. So you see, this happens up there on the principal bundle, but here in our down-to-earth formalism so far, we're still considering functions on the base space. Okay? However, this function on the base space is not a function on the space space. It's a field, a C-valued field, okay? And hence we can have this additional term here. We'll have to take this into account. So I put this in the cloud because when we later on want to make the transition to this, we'll have to take into account what this psi is. But the moment we treat it like this, it's being derived by a covariant derivative. Now, however, what would happen if we apply the same momentum operator to a function for an f which now really is a smooth function on the base space, which we can say is Rd as a manifold, okay? Well, in that case, it's just minus I del alpha f, right? Because only sections of a bundle, only on there the covariant derivative acts with an extra term. On functions, it still acts like this. Okay? So, well, with this insight, let's define the Q alphas like before. It's R if we're the first coordinate, and it's theta if the coordinate is the second coordinate. And let's check what's Q alpha, comma, P beta acting on some psi. Okay? So in principle, we have to go through all the various options. Well, let's try that. So it's, let me call this, how do I call this? Little q alpha, but qr is r and q theta is theta, and that's a function, okay? Q alpha, then is a minus I. Now comes the covariant derivative, right? So that's the, let me write it like nabla beta. That's what we used before. So this, if, yeah, well, this is the nabla alpha here. Nabla beta acting on psi minus I is plus I. Nabla beta acting on Q alpha psi. Okay? So now the question is, what happens here? Well, this is a tensor product, but careful. So this is a, well, if you want a vector, because its values are in the bundle, in the fiber, right? But this is a function. And that's the point. So nevertheless, that doesn't free us from the Leibniz rule. So minus I del beta psi plus I. Now let's write down. So it's the Leibniz rule. It first acts on this guy, and this guy is unchanged, plus I. This guy stays there with a tensor product, if you want, but and it takes this form. But now, because these are really functions, because r and theta are coordinate functions on the manifold, this simply becomes a del beta q alpha, right? Whereas this guy stays what it is. But in any case, there's a plus I, there's a minus I. This guy cancels against that guy. And because this is just a function, this is a delta alpha beta. Because it's the r by r or r by theta and so on. So this is nothing but I delta alpha beta psi. Hooray! Hooray! So although we modified this guy by an extra term, which if you looked at this naively and didn't understand that this is a covariant derivative that acts differently on vectors, it's an element of a vector bundle, acts differently on vector fields than it acts on functions, you would be stuck here because you would have to decide how this covariant derivative, and there's an omega term, you wouldn't get the delta. But this is a function, and this is a vector field. Okay, it's a difference. A vector field being a section of this vector bundle, right? Hence, this works. So it's crucially important to understand that a covariant derivative, I wrote it down before, a covariant derivative on a vector, it acts very different from how it acts on a function, because on a function it acts trivially, but on a vector it simply doesn't. Okay? So only by the view of covariant derivatives and bundles and so on do you actually get these two things to work together, the self-adjointness and this result. And the other commutation relations you can show similarly. Okay, so we seem to have an insight here. This whole idea somehow works. The question is, does it only work for polar coordinates? Maybe polar coordinates are so simple that it works. Maybe it only works in 2 dimensions. Now we had to fix some numbers there. One could worry, if I go to higher dimensions, I do not have enough numbers to fix, and so on. So I'd say after the break, we try to investigate how this works in general coordinates. In the break, I realized we just made a mistake, but you didn't realize. So we started with psi p alpha phi, and we calculated that this is something which I claimed, and that's the mistake, I claimed this was p alpha psi comma phi, and then we had 2 extra terms, and they were in principle correct. So can you tell me the 2 extra terms we had here? Exactly. So this is what we had, and I asked you how to match the omega such that this cancels and this remains. The problem is this term I got from another term that was written there before, and that was the integral of dr d theta minus I del alpha psi star phi. Agree? Now the problem is this isn't p alpha psi, because the p alpha now has an extra term if it acts on a psi. Okay, so I prematurely identified this with what I wanted, right? Okay, great result, unfortunately wrong. So let's do it right. Let's do it right. Okay, so this is dr d theta. Now let's write what we want to have. We want to have that this is del alpha plus omega alpha acting on psi, then starred on phi, plus the other 2 terms. But I now didn't write what is here, so I need to correct this. Now, what's the correction term? Okay, so what did we add? We added, okay, minus, I be careful. So dr d theta, I think there's another r here, no? There is an r here. There's an r here. Yeah, okay. So dr d theta r, so I take away what I added. What I added was minus I omega alpha psi starred phi. Do you all concur? That's what I added, and I subtracted again. And then there is a plus I dr d theta psi star phi minus I dr d theta r omega alpha psi star phi. Aha. So now the whole thing presents itself somewhat differently. I have a minus I that's being starred, that's a plus I, which I take to the front here. Now I write this as an omega star psi star, because that is what it is. Okay? So I have this guy here. And now I see that this term and that term, they're the same up to the fact that here's an omega, an unstarred omega, and there's a starred omega. Okay? So now these two terms together need to cancel this term, and this is certainly effected if omega r, because omega theta is 0 anyway, is if omega r plus omega r star plus omega r must be 1 over r. Agree? So that was the mistake. That was the mistake. Okay. And so that's twice the real part, no? Okay. And what do we do about the imaginary part? Set it to 0. We could leave it open. Well, that's what we read off from here anyway. Okay? That's what we read off from here. Now, if we look at the... I'm sorry, so this was the result we had from before, but we only had this result if the alpha was r. Isn't that right? So this is only for the alpha being r, the r derivative. Okay. Fine. Omega r, omega r, omega r. So this is the omega r. Yeah, that's okay. Good. Good. Okay. Anyway, so that was what we wanted to see, and we can choose the imaginary part to be 0, and nothing changes. Everything works out fine. Okay. Good. Okay. Now. We already checked the commutation relations. Commutation relations also work fine. So now let's look at the general case. Okay, so this was just our introductory example where we detected the problem, and now we want to do this in more generality. In more generality. Well, so if we go to so let's look at an integral d to the dx, where x are some coordinates. I propose to write a determinant of a 0,2 tensor. I indicate this by 2 dots down here. So let G be a section of the 0,2 tensor bundle over M over the base space, with the property that if you plug in two vectors, that this is the same as plugging them in the opposite direction. So this is for any x, y being vector fields. And I also propose that if x, y, or I require that if x, y equals 0 for every vector field y, but you can also do this pointwise, then already the vector field x is 0 everywhere. In coordinates on a patch U of M, this amounts to the fact that the coordinates, that the, what indices do we use so far? None, okay. That the coordinates in terms of the components of this 0-2 tensor fields, in terms of this, are, of course, symmetric, like this, and the matrix G alpha beta is non-degenerate, but not only that, it has positive signature. So that means that there exists a coordinate system, and that means there exists a transformation at each point, a frame at each point, such that alpha mu t beta nu, this being the coordinate transformation, equals this matrix, and that's Sylvester's theorem. And that these are all positive comes from here. Okay, so this is nothing but a standard inner product on this manifold. And these don't need to be, I'm sorry, these are not coordinates which produce, there are frames at every point that produce this. There may not be coordinates that produce this in an extended region. Okay, anyway, we now consider our base space M to be equipped with such a 0-2 tensor field with a metric. And such a thing is called a metric manifold. So if we take a smooth manifold and equip it with such an object, this is called a metric manifold or a Riemannian manifold. Okay? And one of the things a Riemannian manifold gives us is such an object. I can take the determinant of this guy, which is funny at first sight because normally we take determinants of endomorphisms index up and down, but this is a bilinear form. Now, nevertheless, we can take the determinant in any frame and get a number. The point is, if we change the frame, if we change coordinates, there will actually be, this will not behave as a scalar. So the determinant of a bilinear form does not behave like a scalar under coordinate transformations. It picks up extra terms. However, it picks up precisely those extra terms. So I should, maybe these components down here, I should make them explicit. These are the components with respect to a particular coordinate system, and I choose the same coordinates I choose here for integration in the chart. Now, the interesting thing is, if you change here coordinates, then you will pick up from here, you'll pick up a Jacobian factor. But you'll pick up the inverse factor from this expression, and so the Jacobian factors cancel. That means, even if you start in Cartesian coordinates, by the way, what are these famous Cartesian coordinates we're always using? These famous Cartesian coordinates can only be chosen in flat space, because in flat space there's even a coordinate system on the entire space, such that everywhere by the induced frames from the coordinates, everywhere the metric takes this form. And what is then the square root of the determinant of this is 1. That is why it's normally never written in Cartesian coordinates. That's why we write these integrals. But secretly, there is a 1 which is not a 1 that remains a 1 under changes of coordinates. However, what it does, it changes exactly the opposite way to the Jacobian from this change. And hence, if we want to write down a volume integral, an integral over an entire manifold, over some function, scalar function on the manifold, we must always include this factor, and then we never again need to worry about the Jacobians that come up. Okay? So that's the definition we're going to use. Okay? So in more generality, we want now to define psi comma phi, this inner product, is this factor times psi star of x, phi of x, okay, this integral. But now for any choice of coordinates on M. Now, if you wish, you can choose M to be Rd, and you can choose the coordinates that make the metric everywhere have this form. Then you come back to the original integral we had. Now, if you have that, you can change coordinates, and then you just have a different coordinate representation, okay, of the same integral of flat space. However, nobody forces you to start with a metric that for which there exists a coordinate system such that it everywhere takes this form, and then this formula still works. And this way we put our inner product on a curved physical space. And hence we're going to do quantum mechanics on a curved space, for instance on a sphere. You could ask, how does an electron that's for some reason confined to a sphere, what is its quantum mechanics? You need to start here. Okay, fine. So we have this, and now with this we're going to redo our calculation from before. So we again assume that we have a p, that we have several p alphas, or now let's call them pi's again, and they're minus, or pj's, they're minus I covariant derivative j, and if acting, and we have qj's that are multiplication with the corresponding coordinate. But you see now the coordinate x1 could be r, x2 could be theta, and this would be with respect to nabla with respect to d by dr or d by d theta. Okay, so we have this, and we know that the application of this guy on a function is just the partial derivative in the coordinate direction, but the application of this guy to a psi is the partial derivative plus the correction term by the corresponding component of the Young-Mills field in the same coordinates. So one form on the base space, this Young-Mills field. Okay. So now let's look again at psi, comma, p. The p made the problem. It's obvious that this multiplication, because it's a real coordinate, this is always Hermitian, right? This is very clear under the integral. So this guy can only cause the problems, as we saw before in the example. And we now apply this, like before, and want to look at this in more generality. So now we have our inner product on our d-dimensional space with arbitrary coordinatization x, but we're calculating in a chart here, of course. But we have here the square root of the determinant of the metric components expressed in the very same chart x, like I wrote down before. This is the short form of this. And then we have the psi star of all the x's, and then we have the minus I del j of the phi. Okay? So now we see before, when we, by integration by parts, pulled over this del j, we had to deal with acting on a c star and on the r that was there in polar coordinates. Well, you can quickly check. If you start in Cartesian coordinates, then you change to polar coordinates. The g will change to, so the g in Cartesian coordinates in flat space was that, and the g in polar coordinates is actually this, right? Yeah?
You're missing the omega, don't you?
Absolutely right. Thank you very much. Thank you very much. Very important. Thanks. Okay. And then the g changes to this, and if you then take the determinant, you get the r squared. Then you take the square root, you get the r. That was the r. There you see, if you come from Cartesian coordinates, you get the r. But again, this is just a special case of this formula because the g could be such that it changes from point to point in any coordinate system because there is none that makes it constant everywhere, which is equivalent to the space being flat. So this is a very general expression here, very general formula. Okay, so this was just the application to, or the reassurance that what we did before fits into this scheme. And now, of course, we have to deal with revolving this over here. So we get a minus integral d dx, and now a plus I, because a minus I, and then we get a del j, but acting on this entire thing. So I write it in a shorter and shorter form. If I just write the g, I mean the determinant of g. And then we have the psi. We can obviously first derive it like this, then star it, because this is real. Then we can pull the I in the start expression. Then it's a minus I, and we have this guy again. Phi. That's this term. And then we get an extra term plus integral d dx square root of g psi star of x omega j phi of x. Correct? So exactly the same idea as before now. We execute this derivative on this product here. Okay? And so we get integral d dx square root of g. So first act on the second term, minus I del j psi starred phi plus integral d dx minus I times d dx del j square root of g. I can forget about the star because this it's a plus I, no? Because of the star. Can forget about the star because this is all real. Psi star phi plus, well, for completeness, what we had before, square root of g psi star omega j phi, right? Please correct my signs if there should be a mistake. So now we again rewrite the right-hand side. Because we have to introduce in the first term our additional omega in order to make this a covariant derivative. So here we have again the invariant volume form here. Then we have minus I del alpha, but we add an omega alpha. And then we only let it act on the psi star, and there's a phi left. We need to compensate for this term, so we need to subtract what we added, to subtract d dx square root of the determinant of g, and we added minus I omega alpha, but the whole thing starred, so we added this guy here, psi star phi, okay? And then we should already have a similar term, so let me take that one first and write it below. Integral d dx square root g, that's the last term from before. And there's an I missing. Let's see what we did here. So we had a minus I here. And I think, yeah, it just went missing, right? This is just a minus I here. Is that correct? Minus I times this guy. So this is a minus I here. Okay? So that's a minus I. Pardon me? Is that correct? Yeah, that's right, that's right. So there's the I from here that goes here 1 2 times. Exactly, thank you, thank you. Okay, so omega alpha psi star phi. That's right, that's this term. Alpha, well, it's a J. Okay, J, 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 J. Okay, and the extra term plus I integral d dx. And now there's del J of this density psi star phi. Aha. So what do we conclude now? We know that this guy here is pj psi comma phi. So this is precisely what we want. So all these terms ought to cancel. So how do we get this? Well, we get this by omega j star plus omega j, but both of them still coming with this factor square root of the determinant of g must be the same as del j of the square root of the determinant of g. Right? In other words, 2 times the real part of omega j must be del j of the logarithm of the square root of the determinant of g. Because I multiply this through down here, and then it's the derivative of the logarithm. So let's check with our, so that's the general result. So for a generally curved manifold, so a general manifold with a, where locally, well, with a metric, and then locally we go to local coordinates, obviously, because we're using partial derivatives and so on. In a local patch, take the square root of the determinant of your metric on the manifold, take the ln and derive with respect to the various coordinates, and you get the real part of the Young-Mills field. So check with our hands-on example. So what did we have there? We had there in polar coordinates, that was GRR, GR theta, G theta r, and G theta theta components, which for flat space, if you just come from Cartesian coordinates, is just 1 and r squared. Therefore, the determinant of G in polar coordinates is r squared. That means the square root of the determinant is r, because everything is positive. We can forget about any absolute value signs. And so then we calculate del j of ln r, right? And this is supposed to be 2 times the real part of omega j. And you know what that is. This is del j r over r. And that is for omega theta. We already take it real. This is 0. And for omega r, this is 1 over r. And that's exactly the result we got before by hand. Obviously, this is the general calculation. But again, before we merely took curvilinear coordinates, in this example, curvilinear coordinates for an anyway flat space. This here is true for any manifold for quantum mechanics, or this inner product on any manifold. But of course, this is still a local expression because we chose coordinates on the sphere. We have to choose a coordinate patch. On another coordinate patch, it looks differently, but of course, this meshes together properly. Aha. Okay. So we were able to write down this this inner product in the right way, such that we were also able to write down the appropriate covariant derivative in order to define this P in the right way. Okay. Now, the challenge, so this looks very good. Okay, so the idea looks very good. This seems to work. We're now able to, we freed ourselves from any such folklore that says you cannot realize these commutation relations and the self-adjointness unless you're on a flat space. You can do it on a curved space. But even if you're in flat space, you can go to arbitrary coordinates, which on curved space you need. On curved space, there are no Cartesian coordinates. That's the whole point. Okay? So this all works pretty well. However, we still have to understand properly where this guy lives. I mean, this is a calculation that works out numerically. Where does the guy live? Well, this is the Young-Mills field, no doubt about it. It has a tangent space index, or, well, it's a covector, right? It has an index down here, which is to the base manifold. And it acts on the psi, okay? So this is the Young-Mills field. So this must be what, if the sigma is the section to the frame bundle that associates with every point a frame, in this case a local section, which associates with every point in this U, where for this U we have a coordinate map x to Rd, we have a coordinate chart which associates to every point the induced frame here. So our psi that we have here is the Young-Mills field under the pullback of this, right, of a section of our associated bundle, but we already saw that the section of the associated bundle is nothing but a function that is vector fiber valued, in this case the C fiber, on the principal bundle. That was this theorem we had, and that's the way we get the psi. So our psi here is still C valued, but it's a C valued function on the frame bundle, well, or rather the pullback of this to this local chart. And hence on this local chart, yeah, it is a complex valued function, but if you go to another chart, it doesn't transform like a function, it transforms like such a pulled back section on the vector bundle, or alternatively C-valued function on the frame bundle. Okay? So this is the first thing to keep in mind in order to understand this thing better, and we'll continue next time with that. So that's the psi. That's the psi on the phi on which we act. Then this omega j is the Young-Mills field. So there must be an omega, a fat omega, living on the frame bundle. So if you pull it down by the very same section that is induced by local coordinates, we're using local coordinates, if you're pulling this fat omega down, you of course get it's a one form on here, you pull it down, it's a one form on there, it has a little j tangent index on the base manifold. That's our little omega j. It's the Young-Mills field of some connection that lives on here. Now this covariant derivative that we have here acting on there, well, that must be understood as the pullback of the exterior covariant derivative of our fat psi that lives up here. Okay? So we have to pull that down too. So this must be the psi we're looking at, and so on. So these are just some thoughts on how now from this calculation, which works perfectly fine on the base manifold, okay, how we relate this to the various geometric objects we have in this game, okay? And the aim is to now make what happens on the base manifold in this kind of calculational, I'm always tempted to say numerical way. Well, it's not numerical, but it's, you know, it's a chart calculation. We're dealing with objects in charts and how they transform and so on. And to relate this and to deduce what the overarching structure is on the frame bundle. And then we get a proper picture of what quantum mechanics is on curved spaces and in arbitrary coordinates. And failing to recognize, and you see that in order to reconcile this with things we know in quantum mechanics, we have to go so far back as to give up the idea of a wave function being a function. Okay? This is just a bad idea. It's just a bad idea. And obviously, if you want to do things like quantum gravity, and, well, if you even want to do quantum matter on curved space-time, well, this is only curved space. But say you had only curved space, and you see, can't be too different, curved space-time and curved space. There is, of course, a difference. But failing to understand this, you have no hope of understanding the bigger question. Okay? But it's something that's already in basic, non-relativistic quantum mechanics. Okay? So nothing to do with the difficulties of space-time and relativity. This is something to recognize in order not to have the wrong idea. Okay. So we might look at this in more detail next time, but I think it gives you the idea how these concepts can help you understand standard issues, okay? And then, it's, of course, always the problem of matching things we know with a formal idea we might have, but one shouldn't start from the formal idea. The formal idea is only the guideline where you push what you already know, okay? And then at some point, you need to match that. Okay, thank you very much. See you on Thursday.